Stats enthusiasts, welcome back to another video in our Unit 5 Sampling Distributions playlist. This is actually the last video that we are going to cover, and it is for a sampling distribution for a difference in sample means. I'm Goldie if you're new here, and I'm going to take you through all about these special sampling distributions and what exactly they entail. So sit back, relax, and let's dive into the notes. As we get into the notes for a sampling distribution of a difference in sample means, I just want to remind us all, why do we have this? Why are we creating a whole other sampling distribution, this time for a difference in sample means, and where is this taking us? So remember, when we compare two things, it's very common practice in statistical inference. We could look at two samples from two populations to see if there's a significant difference between the two populations. So when we're using means, we're looking at something quantitative between the two samples to see if there's a significant difference. Or we could be looking at two or more experimental treatments to see if the difference that we observe is due to natural variation or the actual treatment themselves. So this comparative statistics aspect is very common. And we'll be answering these questions in the coming units once we learn a little bit more about inference. But inference, the basis for inference is a sampling distribution. This idea that averages do not vary as much as regular variables, and that averages are very predictable in the long-term distribution. So before we get into the difference in sample means, let's recall quickly the sampling distribution of a sample mean. So remember that the sampling distribution was approximately normal as long as either if n was less than 30, the population distribution should be normal, or if n was greater than or equal to 30, the central limit theorem says the sampling distribution will be approximately normal. So far, those are our two guidelines. Now, as we move into statistical inference, those guidelines are just going to change a little bit, but this is the foundation for it. Okay, shape. Center. The center of our sampling distribution is going to be equal to our population center, as long as either we randomly selected or randomly assigned, depending on the situation. And then our spread, we have this formula for calculating the standard deviation of a sampling distribution for means that's based on the population standard deviation. And we could use this as long as n was less than or equal to 10% of our population. And this, again, just means we can sample without replacement without affecting our population too much. So that was our sampling distribution of X bar. So now let's get into the sampling distribution of a difference. So now we're going to have two new notations. We have X bar still, that still represents our sample mean, but now they're going to have subscripts. And usually they're 1 and 2. Remember that these subscripts can also be letters. They just help us identify our two groups, whatever they are. So we're going to have those two subscripts because we're going to have two groups now. And when we look at the sampling distribution, let's talk about the shape, center, and spread. So the shape, spoiler, is approximately normal, okay? Go figure, right? We've talked about how when we combine two random variables, if those two random variables are both normal or approximately normal, the combined shape will be normal, approximately normal in our case. Now, this is as long as both sample sizes are greater than or equal to 30. We can use the CLT, or if one or both are less than 30, each population should be normal or approximately normal. So remember, that's our guideline. Now we just have to check it for two groups. Okay? So it's the same thing for one sample mean. For a difference, we just got to check it twice. Okay? For our center, okay? Now our center here, we're going to have two population centers, mu sub 1, mu sub 2, and the center of each individual sampling distribution is going to be equal to that. Now, again, we kind of have subscript soup here because I have mu as my regular variable. And then in my subscript, I have X bar sub X1. So I have kind of like three subscripts going on. So when you write it, when you see it, it kind of looks X sub 1, like X sub 1. Okay. mu sub x bar sub x sub 1. It can get a little crazy, but just remember what the symbols are trying to tell us. This is the center of the sampling distribution of the first group, okay? And to find the difference, we just subtract those two centers. And since both of those centers are represented with their population mean, we just subtract their population means. Now, this is, again, as long as both samples have been randomly selected or there's random assignment in the experiment that you are looking at. And that's going to be your center. The last one is your spread, okay? And this is where it gets a little crazy, but let me show you, before I show you the formula, let me show you how we get to the formula. Remember that each sampling distribution, each group has two standard deviations here. So everything, this is the formula we just went over for our spread. It's just now it has a subscript of 1, and over here now it has a subscript of 2, which is fine. So we're going to bring those together. How do we bring standard deviations together? Hopefully you're screaming into your computer that we always add your variances. Okay, whether you're finding a difference or adding them together, a sampling distribution is going to be a difference. We always add variances. So this is kind of the skeleton template we have here, the square root of both variances added together. So to get the variance, we square the standard deviation. So in parentheses, you're going to see I'm going to put each of these standard deviations. Okay. Once each of those go in there, I can just simplify it a little bit, right? So the numerator gets the squared, and then the denominator also gets the squared, but it's going to cancel with that square root, okay? And that's why the formula you're going to see, be very careful here because we have a subscript and a superscript exponent. So we have sigma sub 1 squared divided by n1, and sigma sub 2 squared divided by n2. Okay, so that denominator square root got canceled out because we squared our standard deviation. And that's the formula for it. And as long as both samples satisfy the 10% condition. Again, as long as you're sampling, right? If you're not sampling, you don't have to check the 10% condition. But if you are sampling, make sure both satisfy that 10% condition and you can use that standard deviation formula. And there's your reminder. If sampling, if sampling, you have to check it. If you are running an experiment, there's no need to check it. Which brings us to our example. We're only going to do one example in this video, and we'll practice more in your assignment. So this example, a study is conducted to compare the effectiveness of two study techniques, A and B, in improving test scores. So for technique A random sample of 80 students has an average score of 85, standard deviation 10. For technique B, a random sample of 100 students has an average score of 82 and a standard deviation of 8. Calculate the probability that the difference in average scores between technique A minus technique B is greater than 4. Okay, so we have a very specific probability we are trying to find here, minus. Now, another thing I want you to recognize is that we are taking a random sample here. We are not running an experiment. So it's a little confusing sometimes because you see this word compare the effectiveness of two study techniques and you immediately think, oh, this must be an experiment, right? But because we take a random sample, we are technically sampling here. This is not an experiment. So we take a random sample of students who are in each different study technique. They weren't randomly assigned to the study technique. It doesn't tell us that they were randomly assigned. It says we have students in technique A, technique B, and we're taking a random sample from each of them, okay? So let's go through. We have our 4-step process: communicate, conditions, calculate, conclude. So let's talk about our communicate first. Communicating, we have to identify our two populations, what we're working with here. And it has to be done in the context of the problem. So mu sub A is the mean score of students using study technique A. Mu sub B, mean score of students using study technique B. Okay. So subscripts A and B, just to keep them straight, we can call those subscripts anything we want. We just want to keep the two groups separate. So that's the first step in communicate. The second step in communicate is writing out the probability you're trying to find in symbols. So for us, we want to see that the difference in average scores between the two techniques is greater than 4. Now, because we're looking at the average scores, okay, between each sample, we are using a sampling distribution and a difference between them. So that's where we get these symbols here, mu sub x bar sub A minus mu sub x bar sub B, because we want to know what's the difference that score is greater than 4. Okay, so that's the communicate part. Now let's get into the conditions. We have 3 conditions: random, independent, normal. So for random, both samples represent a random sample of students from each technique. So they told us it was a random sample. This condition is satisfied, which means we can find the center of that distribution. So the difference between the two is going to just be their respective means subtracted. So 85 minus 82 is going to give us a difference of 3. Now we look at our independent condition. Again, because we are sampling, we do have to check this condition. So we look at 80 being less than or equal to 10% of all students using technique A, and 100 being less than or equal to 10% of all students using technique B. We will assume this is a fair assumption because, like most problems, we are not given a population size, but we need this to be true in order for us to do that sampling without replacement. So we're just going to assume this is a fair assumption. We show that we checked it, and then we're going to find the standard deviation of our difference. So here's the formula again that we will be using. And you don't necessarily have to write down the formula again, but I just want to show you that's what we're using. We want to show the values substituted into this formula, and then we're going to find out what our standard deviation is. So we're going to substitute in both of those standard deviations, 10 and 8, and then make sure we're dividing them by our respective n values. 80 and 100 were our sample sizes, and that results in a standard deviation of 1.378. The last thing we want to check is our normal condition. Now, we're not told anything about the distribution of scores. If the scores are normally distributed, skewed in any way, we don't know anything about the population. But luckily, both sample sizes are greater than 30, which means the CLT is going to tell us the sampling distribution will be approximately normal. Okay? We take a large enough sample size, the CLT, the sampling distribution, will be normal. So we have it. We have created our sampling distribution. So now we're able to find this probability because we know that this difference, again, I know it looks like alphabet soup here, but remember this difference in the sampling distributions, we know it's normal, has a mean of 3, and has this standard deviation. Our 3 conditions just showed us these 3 things. From here, we find our z-score. Okay, so remember, we haven't been writing down our z-score formula, but remember, this is what it is. So we take our x value, our mean is 3, and our standard deviation is 1.378. So by standardizing and putting it into a z-score, we change this alphabet soup into just a z. Okay, we solve that, and we get a z-score of 0.726. I'm drawing the curve because I'm a visual gal. So we put that z-score on our standard normal, and we shade above because that's the area / probability we're trying to find. On our calculator, don't write down the calculator speak in your work, but on your calculator, this is what you would put in. Lower boundary, upper boundary is infinity, 0, 1. And then write down what that probability is, 0.234. And then we conclude. Okay, so that was the calculate part. Now the conclude part, we put the context to our answer, and we say the probability that the difference in the average scores between technique A and technique B is greater than 4 is 0.234. And that's our problem using the 4-step the 4 C's for those problems. Now, for these problems, we are just finding probabilities. In the next couple units, we are actually going to be drawing inferences on these probabilities. So our conclude here is just kind of a statement of like, yeah, this is our probability. But it's really in the next couple units where we look at how are we going to use this probability to answer some deeper questions. And that wraps up our video on the sampling distribution for a difference in sample means. And in fact, that wraps up our entire playlist on Unit 5 sampling distributions. Looking ahead in Unit 6, we are going to actually get into inference. So using these sampling distributions, Unit 6 is all about using these sampling distributions for proportions. And we're going to look at confidence intervals and hypothesis testing for proportions. In Unit 7, we're going to use the sampling distributions for means and apply it to confidence intervals and hypothesis testing for means. So that's what you get to look forward to. You can check out my playlist on Unit 6 and Unit 7 when they are available. In the meantime, if you like this video, please go ahead and click the like button and subscribe to my channel for more AP statistics content. I wish you endless statistical success, and I will see you in the next video.